a number of years. Jim has been on it for even a lot longer than I have. I've been with X for about 2 years now, and my background is in statistics and data science, and I've generally always worked in the agricultural space. We have a similar system, I think, maybe to what you all have been developing for phenotyping, and we do a few other things as well in agriculture. But maybe I'll hand it over to Jim, and he can introduce himself also.
Hello everyone, my name is Jim, and I'm leading minerals engineering team head here at X. So I have been Google for about more than 10 years, so long enough. Yes, as David said, and I have been this project for about 5 years already. I actually personally one of the first engineer actually started this project. Yeah, happy to meet with the guys and happy to provide insights if we can. Thank you.
Thank you. Abraham, are you going to start or is Grace?
I'm going to start the presentation. Hello, everybody. Hey. My name is Josep Baca. I am a mechanical electrical engineer, and I am in charge of the mechanical design and manufacture of the Berrybot project. For this project, there are 9 main areas. We can start with interface design and data visualization, agricultural mission, central control and data management, artificial vision, power and energy control, autonomous navigation, project management, mechanical design, and finally, communication system. For this presentation, I'm going to give a pass to my partner, Grace Sevillano, that is going to follow.
Hi, my name is Grace Sevillano. My main interest is artificial vision, like you can see in the next presentation. I have a bachelor degree in electronic engineering. Well, we start with a presentation.
If you, Grace, if you want, I can share the presentation.
Okay, it's better. Okay, like my colleague say, we have 9 areas. Well, the next, for the area the challenge of agriculture in Peru. Peru is characterized by being a country with high biological, climatic, topographic, and social diversity. The heterogeneity of geographical condition implies a challenge for agriculture, which must overcome inhospitable climates, little access to water, the presence of pests and terrain where mechanization is very difficult. In this scenario, thanks to the management of mega irrigation projects and investment from the public and private sectors, agri-industrial activity has established itself as one of the main axes of economic and social development in Peru. Next. Thanks to the growth of agro exports, Peru is considered one of the 10 main food supplier countries in the world. In 2020, the export of agricultural products reached 7,309,771,000 FOB. The main destination markets being the United States, Netherlands, Spain, and also United Kingdom. Among the main export products, we find avocados, grapes, citrus fruits, asparagus, and in recent years, blueberries present the highest growth and was positioned as the second product with the highest FOB value. Maybe 978 mile and $501,000. The Peruvian blueberry industry is propitious space for the generation of technology and innovation, which promote the sustainable development of the sector in a post-pandemic context. for the benefit of thousands of Peruvian agriculture workers and millions of consumers worldwide. In this context, automation of certain activities by artificial vision and machine control vehicles may be a reliable option in agriculture system with high profit margin, such as the blueberry crop. The BerryBot project goal is to develop an autonomous control vehicle to help fruit counting and yield estimation and pest detection and control. Next, please. Agricultural mission. This area provides technical support to the other areas in crop production and pest management, guiding and refining the project's objectives from an agriculture point of view. In addition, this area share of establishing a connection with blueberry producers and potential users of the technologies developed by the project. As an area of the main achievements was to select blueberry as the most appropriate crop to target the activities of the BerryBot, and to select fruit counting and pest detection as the most feasible and demanding activities that the robot should fulfill to provide efficient support to blueberry growers based on the problems of our agriculture reality. Likewise, this area identify and establish contact with a blueberry producing company that gave us access to their facility in Lunahuaná, Lima, and allow us to collect the information that the other areas need to develop their work, including the measurements of the planting frame and the blueberry fruit data set. Next. Mechanical design. The development of BerryBot has gone through many changes. At the beginning, the model was focused on crops that didn't exceed the height of 1 meter. This allowed the model to go through 2 rows between crops and the implementation of a robotic manipulator on the top. A second revision of the model and the fact that the chosen crop was blueberries made us change the design for a more compact one. Even though this design had in consideration all the geometric limitation of blueberries crops, it was too heavy. So for the third model and the last, a light version was designed that also considered a 5D of a robotic manipulator on the front. Next. In the development of the mechanical design, the commercial software SolidWorks was used in order to validate the mechanical laws. That simulation software was ANSYS used. As for the control of the robotic manipulator, Simulink was used also. Next. Currently, we are in the middle of the manufacture of the first prototype. This first prototype is scheduled to be finished in October. Next, communication system. In this area, their main objective is to ensure the exchange of information between the rover, the server, and the control center. For this purpose, we have made different proposal diagrams. The one shown below is a version that contemplates areas without mobile network coverage. In the first type, we propose to use LoRa modulation to provide bidirectional communication between the rover and our gateway. In the second, it is proposed to use only the cell phone network. This is due to the differing advantage of using this network. Next. On the data transmission side, we use a Raspberry Pi 4 that uses the Wi-Fi protocol to send information to the portable router, ZTE-MF920U, which will have a SIM card to connect to the mobile network and thus achieve the sending of this data to the server in Azure. Regarding the cloud, we have implemented an infrastructure that makes use of some Azure service such as IoT Hub, Function App, and Azure SQL to be the gateway. Management and storage of that data respectively. At this stage of the project, we have simulated data that has been sent to the server and then visualized in a Power BI, which used as a test of the full functionality. Finally, our main limitations are limited Azure storage per educational subscription, limited device processing for image compression, reduced bandwidth of LoRa equipment, difficulty in establishing connectivity in rural areas. Next. For the interface design and data visualization app, basically we aim to do is an application able to monitor data from that robot, easy to find and understand for the final user. That's why we divide into four main screens, which are login, home, dashboard, and maps. In the second one, it's possible to see real-time data from the robot as well as from the environment. In the third one, there's the historic variables data. And in the last one, we can see where the current position of the robot is and where it has been in the last moment. Next, please. We develop the software with Android Studio programming in Java, and we use GitHub to collaborate with each other. Also, we use Google Maps APIs, and we design our UI in Figma. We had some critical limitation related to the development. For example, we don't count on Google Service license, so it's hard to use Google Maps service. Moreover, when we want to get our ideas for the team, we don't take advantage of our time correctly because at the time we don't have license for programs such as Adobe XD or just in NIMD. So we use other simpler tools to design the IU. Finally, right now, we don't work exactly in real time because for this application it's necessary to click on the refresh button, but we will prefer to work with any real-time dataset manager as Firebase database or Azure Cosmos DB. Next, please. This is the this is the login, the first part of the app. Can you please click in the...
Can you expand the window, please?
Yes. Maybe you can run for 2. Yes, that is the app mobile test. Okay.
Okay, you can go to the next one.
Yes. Just escape. Well, the next area is autonomous navigation. That area trying to adapt a base self-driving architecture to agriculture environments. We want, as our area, to use a main camera, the sensor layer that fits the perception layer for the detection model and other sensors such as GPS or an IMU to improve localization. Then this model fits the planning layer with the information of detect crops, rows, objects, and free space for route planning. and define behaviors to obstacles and other moving objects. Finally, according to this layer and the provide or generate map, it used to the control layer to calculate the commands to the robot. Next, please. We have been working on the detection model using some segmentation algorithms from classic computer vision technique, such as thresholding in HSV or other color models, Kenny H detection, hue transform, to some deep learning architecture as UNet, Deep Lab, and knowledge distillation. In this process, we know the need to collect more realistic data according to the data that the robot's camera will obtain in the navigation process. For this, we are using the OpenCV library and the machine learning framework PyTorch and TensorFlow Keras, and for the labeling task, CBAT. Next, please. As you can see in the video, maybe you can expand the... yes. As you can see in the video, we have a basic simulation of a crop file in which the robot model proposed by the mechanical design area is traversing it. In this environment, we are going to test some mapping and localization algorithms such as AirTAB. In the image, well, this is the simulation. Yes, can you? In the image on the side, we have a point cloud resulting from the simulation of the stereo deep camera that we are going to use for the mapping algorithm. This simulation will also be used to generate some data for a subsequent behavioral cloning navigation system. For all this, we are using ROS, Ignition Gazebo, Python, C++. Our currently limitation are high latency for training medium, large image data set located in Google Drive when we're using Google Colab, and limited resource GPU when training in personal computers. To collect better data set, we need to travel to crop fields and label match data. A limited simulation environment to test the algorithms. Next. The artificial vision. From the artificial vision side, we start with a construction of the first data set containing two types of image, like you can see. We have 177 image from two different sources with different illumination. Then we manually label the image using label IMG, supervisedly BGG image annotator software, both for instant segmentation and detection boxes. Now we are running different types of algorithms. Among the most relevant ones are Mask RCNN and YOLO for real-time detection. We are using as Python language, and for machine learning frameworks, TensorFlow and PyTorch. For the tracking and counting of blueberries, we are implemented the XOR as a first alternative. And later, these algorithms will be implemented in the Jetson Nano for field testing. One of the main limitations, like autonomous navigation area, is when we are training, we have a limited GPU provided by Google Colab. Another limitation we have is that we don't have repositories where to store our data. And also, we don't have virtual machine with that computer power. Next video. The video show a test of a first segmentation algorithm with only 10 label image using a Mask RCNN architecture. And next. And the other, the next, yes. Well, this is other video for testing segmentation with the 100 label image and with another architecture. Next, okay. Central control and data management. In this area, interconnecting different areas or PCBs by a cable. This cable is a 4-wire cable that communicates in RS485 format. We have reached 4 documents. First is architecture of the areas, but mainly the architecture of the connection of the PCBs is in an electronic level. Second is POST, power on self-test. The third is communication frame. Here we write a different question and answer that any slave should answer when the master asks as a central control question. And the last list of errors. This list is used to know the current state of each board from any area. This function will probably be implemented on a second stage of the project. And next, please. In the frame picture, we can see some example of question and answer. The question are called, for example, N capital is the representation of a node, then the address of the node, then the separation with a colon, and the type of question, in this case, RC capital question. And finally, the semicolon to determine the end of the string. In the answer, the code is as follows: Rn in capital for response from node. Then the node number, then the type of question, the slave in answering, colon, and then the data, and finally the semicolon. Yes. That's all. Joseph, can you?
Thank you, Grace. I don't know if David or Jim has any questions for us.
I mean, let me just jump in and say, like, I'm kind of blown away by the amount of work you all did. I mean, it's a big group here on the call, but yeah, I'm just so impressed with the breadth of the activities you were involved with and all the various different components of the work that you've considered as part of this project. So, you know, congratulations to the team on what's been done. It's very impressive work.
Thank you.
Yeah, I just want to jump in and say yes, congratulations. Very, very big scope, very ambitious. And I think if everything landed, it could be really, I say, moonshotty. So congratulations, right? Thank you very much for showing such a good picture to us. Thank you. Yeah. On the other hand, we actually don't have too much question. We intentionally don't want to ask any question because in certain ways, so we are working in similar areas. We don't really want to invite a lot of unwanted knowledge from you guys. Be fair to you guys, right? So that's very clear. But we are happy here to answer your questions if you have any.
All right. So then we can start with the questions. We will start with Luis Llerena.
Okay. Hi, my name is Luis Llerena. And the first question would be about the central control and data management. It's how to divide the groups. We have many groups, but for this kind of project, how to divide groups? How do you recommend dividing? How many groups should be recommended? And also how many boards or PCBs should be used as a maximum?
So let me try to answer this question. First, disclaimer, I'm not expert in hardware, so take it with a grain of salt. I'm trying my best. I think in the end, you have to look into what is your goal, right? Is your goal providing something really scalable for your customers? Or is it something at this stage is more research-ish project? And that could actually get your thinking of this process. Some optimization, is that premature? Or some optimization should happen at this stage? I won't comment on specific things that you are doing. Is it good or bad? In the end, my experience is nothing is really good or nothing is really bad. It's always tied with your goal setting. if you are really thinking a more research thing, then a lot of optimization, you probably should forget about it, okay? Because with a lot of bags, you won't be able to move quickly, and having a lot of segmentation is probably only going to slow you down instead of moving faster, okay? On the other hand, if you believe you are pretty close to deployment, that you want to deploy something real in your customer field, then those optimization thing and those, I would say, more realistic engineering part will surface, and that will become your main problem. Hope that makes sense.
Okay, thanks. And second question, also technical question. Which protocol or frame is used most in communication boards? It means PCBs, which is used inside a robot. We are managing RS485, but our alternative were CAN and E2C, sorry.
On this one, I would say there aren't actually many of industrial, standards. There CAN bus is definitely one of them, right? So I would say follow the industry. This is probably my best suggestion. And it's risky for any of us to actually invent something while push forward, especially considering you guys probably are very early in the stage, don't have much influence. So following something that industry is using, that's what I would be recommending, especially look at all these big machinery company. What are they using? I think that probably will give you some hint about how you move forward.
Okay, thanks.
All right, then we can move forward to the next question. John, are you there?
Yeah, good afternoon. Well, our question is more about, for example, here in Peru, we have different areas, the coast, highlands, jungle, and we don't know exactly what type of technology we can use to transmit data and image. So our question in specific is, what communication technologies can we implement in areas without a cellular or Wi-Fi connection to send image and numerical data?
So I think here we are in US, we probably are having a very different landscape than what in Peru. So I don't really know the Peru's infrastructure to have a knowledge that educated answer to your question. But a naive rule of thumb to me is really thinking infrastructure is really expensive, right? So building infrastructure is probably even very, very prohibitively expensive for a lot of countries. That's my guess. So think that way. So if you think what is a bigger problem? Is it having all this infrastructure in your field a bigger problem, or building a robot a bigger problem? Then you probably have an educated way to think which way you should pick. Do you want to pick the harder way or pick the easier way, right? So that makes sense?
Yeah, but I don't know if there are some technologies to use in this type of areas. For example, one of our suggestion or proposal is to use LoRa, for example, because LoRa we can send a large distances. So I don't know if it's the best choice to use LoRa in this type of communications.
I get it. So there were always a lot of different, other technologies that are flowing around, right? So take it this way, right? You guys are doing something difficult, and if we are building something difficult on something already other people are also doing difficult things, it's just bringing risk into a project, right? If you are depending something mature, your risk is low. If you are bringing something more riskier, your project is just more risky. So I think in the end, I don't have a good understanding of our Peru's infrastructure and the technology landscape or other partners, right? So think you want to depend on something very mature so that you have a less risky factor, or you want to develop everything on a broader, I would say, breadth of very risky technologies, and you still take a motion, right? So in the end, someone who's running this project have to make a risk assessment call to determine what is the maximum risk you are willing to take, and then go from there.
Okay, thank you. I get it.
Hey, if I were to add some at least previous knowledge on this topic, I used to work on a project called Makani, and we used to fly our kite in Hawaii, and we didn't have much service there. We had 3G, it was very slow. We were generating a lot of data and a lot of videos and images where it was impossible to upload it through 3G. So along the lines of the thing that Jim was saying, we were not there to fix the infrastructure of internet problem. That wasn't our job. Our job was to fly the kite and make it work. In your case, your job, I guess, is to run your robot and collect data and analyze it and make decisions. You're not there to solve the internet problem in Peru. That's so. In our case, for example, we had two sort of alternatives to do, and we used to play between them. One was to save the data in a hard drive, in a USB drive where you have internet, and then upload it. And then your scientists can analyze that at the university, if you download it there. If you do need real-time data, we had to make the choice of, we can't do that there. It's impossible. So we had to find a new location where we could do that in real time, somewhere closer to our office. So that would be, I guess, a suggestion that I will say is, if you must be in the mountains where there is absolutely no service, you will have to come up with a plan to download the data, go to the closest town, upload it, and then you can analyze it later. And if you do need it in real time, I wouldn't spend much energy trying to fix a connectivity problem in the mountains of Peru, because that's going to take you years. And that's not what you're trying to solve. So in that case, see if you can find alternative locations where you do have connectivity to do real-time analysis.
Yeah, thank you, Luis. That's very right. The next question is, for example, like I mentioned, we are planning to use different system communication with a low bandwidth and low data rate. And we are planning to use or implement an image encoder and decoder. And our question is it the best idea to use an image decoder in the cloud, or we are considered to use an edge computing?
So I would say you should also take a cut of what is the pros and the cons, right? So I think cloud is perceivably is much easier environment, right? So a lot of tools are there. You can do a lot of things. Edge is perceivably very much different space, which requires a lot of in-depth knowledge and hardware setup. So I think you have to decide by yourself, what is the right way for you. Right? So are you going to take a much bigger risk, doing something much harder, or which actually may work for research stage project, because that's where, because you're shooting for a very, very high bar, right? So you want to do something really, really difficult. Or you want to say, take some more iterative approach, doing something simple and go from there and iterate, right? So that has its own benefit, but also downside that will slow down you for sure, and you're probably going to build quite a few knobs that's not going to be needed down the road, right? So to me, I'm not running this project. I'm not going to make a risk assessment call, but these questions is always a trade-off between how much you are really invested in research and how much you are really moving toward doing some kind of more realistic production. Does that make sense?
Okay, so we have to consider the data, you mean, right?
I don't get it part, but what I'm saying is that cloud is probably much easier to do, but less risky, but it's probably further away from what you really want to do in the end. Going to edge directly is probably something that you want to go into in the end, but my suspicion is that it's going to be much harder and probably 5 times harder than you do in cloud. That's my guess. And how you are going to take a different approach is really it's all your own choice.
If I can build on what Jim is saying there, I think if you start building these models in the cloud, you can possibly iterate much more quickly. You can learn more about what's holding you back in terms of the performance of the models and so forth, and then later optimize down to something that can run on the edge. If you stay in the edge the entire time, you might be iterating much more slowly, and learning the learning rate will be a lot less than as a result.
But again, right? It's really you should align with your goal, right? If your goal is really go this step further, right? You don't want to spend too much time in exploration, which may or may succeed in the end. So so your strategy could be different.
Okay, thank you.
All right, then we can keep going with the questions with Tavi.
Yeah. Which testing tools should we use for this application, and how should we implement it?
So I think the question is vague enough. So honestly, my first reaction is I don't know. My guess is there's no existing tool that exists. So from Google standard, every single testing tool is built together with the development, because only developer knows the best of what this tool is doing and what to test. So my guess is that if you really want a reliable tool, you will also want to develop a testing tool for this thing, which doesn't exist. And my hunch is you won't find it.
Yeah, thank you. That's a good answer.
Then we can keep going with Eduardo.
So I'm not sure if Eduardo is here, but when I saw the simulation environment that you demoed in the talks, in the slides earlier in one of the videos, it did remind me of there was an event earlier this year called the Field Robot event, which was held by a group in Europe. I'll put a link in here. So they have a simulation environment, not for blueberries, for corn, I think, but that might be a similar type of an environment that you could use for navigation and so forth with robots like this. So you should check that one out.
Thank you. We will check that. Well, then we can keep going with the next question, I think. Well, for the next question, do you know how we can obtain digital elevation models to simulate different terrains for various crops, fields? Any open data set that has high resolution digital topographic data, or will be better to generate from sensors like LiDAR or cameras?
Yeah, really good question, Eduardo. I don't know of any offhand where you can get, I'm guessing you need pretty high resolution elevation models here. You can obviously get, country level maps, but they're at 30-meter resolution, which is not going to be sufficient. I would just encourage you to check for academic groups that may have published a small data set like this for a particular field, and then use that and work from there or simulate from there to get other examples.
All right. And then we can go to the next question. Okay, which embedded computer do you think will be the most suitable for the implementation of the navigation system? Do you think a Jetson will be a good fit, or what others would you recommend trying?
Can you hear me now? Sorry.
Yeah, we can hear you.
Yeah.
Sorry. Okay.
Okay, so this one I can tell you. I'm confident. I'm confident. What I'm going to tell you, whichever it is today, is going to be wrong in tomorrow. Okay, so that's what I'm super confident. And so this is in certain way it's a bet. So how much confidence you are in certain platform, right? Jetson could be a good bet, and the Texas TI platform Snapdragon could be another good bet, right? Then some sort of ARM platform could be yet another good bet. So I'm not a prophet. I cannot predict future. But my hunch is that NVIDIA probably should have a good share in the future, say 2 to 3 years. So I will put some confidence in NVIDIA, and I will also put some confidence in Snapdragon chipset just because of the cell phone industry, right? So, but if you ask me which one is better, honestly, I cannot tell you the truth, because the truth is that if I can predict that one, I can buy their stocks today and I can retire in 5 years. So this one is super hard. Whatever I'm going to say here is going to be wrong. So.
Okay, thank you for the input. Then for the next question, Eduardo.
Okay, the next question is how to handle large image datasets for training different deep learning architecture for segmentation. We try to training a dataset using Google Colab, but we have a high latency when the data is located in the Google Drive. So, do you?
Yeah, that's why I'm going to tell the truth, but you won't be liking it because the truth is sometimes it's hard. At this moment, I think only 3 companies on this world, actually 4 companies, can really deal with the kind of really large volume data sets. It's Google, Apple, Amazon, and Microsoft. So the reason is that you really want to have a reliable model or reliable some sort of training infrastructure and inference infrastructure. You really need a very, very big infrastructure and the computing footprint everywhere. Okay. So I think at least probably across globe, there's only very few companies, US included, there's only 4 of these companies can really do all these things in-house through a very, very seamless way. Google has spent about probably billions of dollars just to build like hundreds of billions of dollars build data centers, and hundreds of billions of dollars to build infrastructure. So those kind of investment, it's very hard for anyone who's really startup to catch up. So your best chance is really going into cloud and obtaining some good amount of training resources infrastructure through either Azure or AWS or GCP. But that requires some big investment of money. So unfortunately, quite a few companies have been failing to secure those money. I feel a good example of a company who's really succeeding is really those auto-driving company who has big and deep pockets, who can really leverage this kind of infrastructure. But for your project, you will really need to think very, very carefully how much you want your platform or you want your algorithm to be generic, right? So that means a lot of investment. Or maybe you can do something smaller scale, more specialized, do something better in just some specific domain area. Yeah.
Thank you. Then can you continue, Grace?
Well, like my before colleague, which embedded computer do you think is the most suitable for the implementation of the real-time detection system? A Jetson is suitable? Any suggestion? Or as you mentioned, processing in the cloud will be easier than on a device as we have been planning?
Yeah, as I said, I cannot predict future. NVIDIA is somewhat a safe bet that you can invest. Because whatever you are going to have committed today is not going to be suitable for, say, 2 years down the road or 3 years down the road, okay? So the specific machine of choice is actually a little moot, or I would say it's irrelevant question. It's really usual thing is that 3 years from now, 5 years from now, right? Do you believe NVIDIA can give you a scalable solution, doing things like that? Or you believe ARM will give you a good solution? Or you believe Texas Instruments will give you a good solution, right? Or you believe Intel will give you a good solution? So invest in all this fundamental infrastructure. You either forget the long-term factor, you pick anywhere at now to do some experiment, or you really should think because investing in hardware, computing platform is a long-term choice as well. You really need to be careful about who you put your bet on, right? So you are a very, very early stage project. You have to put some bets, and this is one of the bets you have to put on.
Okay, thank you. Then next, how could the recurrence of blueberry be solved in the counting algorithm? Because in the camera will go back, it will count the blueberries again, and this is a big problem. How can we solve this?
So there are papers out there talking about the counting of small objects, and then people have various degree of success, right? So high level, you can put things this way: you either develop a very sophisticated model, right? So the current model might be just too small, you know. You just need to increase the model capacity very much to deal with all these very complex scenarios, or you improve your sensor capacity, making sure your sensors are really capturing very good data with multiple occurrence or multiple view or any of these things, right? So you either improve your information or improve your model capacity. So at this moment, I don't think there's any good answer for you, and it really depends on how you are really thinking of these problems. And another way to get out is maybe you should really start thinking, can I simplify my problem, right? So that's another way of you can back it up. That make sense?
Yes. Thank you.
And now, Eduardo.
Okay. Do you think Visual Graph Slam algorithm as RTAB for stereo deep camera will suit well for mapping an outdoor agriculture environment? Or do you think we need to use better algorithms or other sensors?
So I think this answer is quite easy. So I think SLAM is there for about 20 years, and various people around the world have been trying this thing for so long, right? So I think you should question yourself, if so many people have tried this thing for 20 years and haven't been seeing success, why could I do it differently, right? So I think that would be your answer, right? So.
Okay, well, I understand. Thanks.
Thank you very much. That's
no worry.
Those were all our questions.
Anyway, so really great questions and a very ambitious plan. So I really salute for all your ambition and hard try. You know, this I would say is a very ambitious plan. It's probably going to take you guys quite a few iterations to really figure out something more realistic. I take a granted you guys might be all realistic, but to me it's too hard. Okay, that's my judgment. Okay, take with a grain of salt. Okay, so one high level approach is that I sincerely suggest that you guys really should start thinking. You know, can you frame a few really big problems or very difficult problems, identify this difficult problem from your project. And then backing from there, can you solve one by one, or can you simplify your problems so that you don't have so many different problems, right? Having many big problems it shows so much difficulty down your road. And it's a recipe of probably not that successful down the road, right? So that's my high level suggestion.
Well, it is an ambitious project, as you have stated, but we are happy that we are working on it, and we hope that in a few years we have a viable product.
You absolutely should understand some rough time for a few years, but as I said, you guys are very devoted and very ambitious, and you should really try hard. And down the road, I think it's a good opportunity for all of you to always keep in mind that I think Astra, it's our ex-CEO, right? He never believed that I can build a moonshot on top of another moonshot. So there's a good reason why we try to avoid inter-project dependency, because building a moonshot on top of another moonshot is super hard. We try to avoid solving many different important problems, difficult problems at the same time. So
I just close with saying, best of luck with the future of the project, and we look forward to reading about your success in the future. and do keep in touch with us. I think we'll be happy to hear more down the line.
Yeah, good luck, and I wish you guys all good luck. And anyway, so you guys are all young, and with this experience, whatever in the future, you will have a very, very different experience, and great experience.
Thank you very much for the input, and we hope that we can keep in touch.
Yeah, thank you.
Thank you, Jim. Thank you, David. Thank you for the rest of you.
Bye.
Bye.
Thank you,
Have a good day.
David. Thank you,
Bye.
Luis. Bye.
Thanks.
Thanks. Bye. Bye.